All right. Thank you guys very much. Thank you for having me here today. Good morning to you. This is probably one of the better venues. I don't think we've had such a great view out that way on any talks that I've given before. So thanks for the opportunity to come up here and talk to you guys. As they said, I'm going to talk to you guys about green roofs, pervious pavements, and stormwater harvesting, and how they can help you meet volume reduction and water quality improvement goals. Just a little outline of my talk. I'll talk a little bit about some of the challenges we face in the urban environment. Then I'll kind of get into some green roofs with cisterns. I'll show a couple of project examples of some stuff that I worked on while I was with the university. I'll talk some about pervious pavements. We did a lot of research on pervious and permeable pavements while I was at the university. And then we'll get into some stormwater harvesting stuff. Again, I did a lot at the university with that. And then we also have a project with Geosyntec that we're going to be doing here shortly. I'll talk about that a little bit and then some general conclusions. So first, some of the challenges in the urban environment. I'm sure everybody's seen a similar graphic to this probably 100 different times. But just to kind of reiterate, kind of in the natural condition, we have obviously rainfall. And we have big amounts of evaporation and transpiration that put water back into the atmosphere, and a lot of infiltration, which contributes to base flow, and not a whole lot of runoff. However, in the developed condition, obviously we have reduced evaporation and transpiration rates. We have a significant increase in surface runoff, which of course brings pollutants, but also makes receiving water bodies a little more flashy and flood prone. Whenever you're working in the urban environment, there's several challenges that you face. One is a lot of times you're dealing with older infrastructure. So you'll come across areas where it was built before modern stormwater regulation was in effect. So a lot of these facilities are not sized appropriately. They don't achieve any water quality treatment goals. And if you're going to come in and redevelop an area, you're still required to meet modern stormwater regulations, which sometimes can be very, very tricky. Just a couple of pictures. Obviously, when we're looking at particularly ultra-urban environments, I mean, there's not a whole lot of permeable space out there. Then we end up with flooding problems, water quality problems, fish kills and stuff. And we use these waters for recreation and important and maybe more importantly drinking. So it really is a valuable resource that we need to protect. Stormwater BMPs, kind of some of the goals of stormwater BMPs is we're trying to reduce the volume of stormwater as close to where it was generated as possible. So the more we can kind of limit the amount of impervious area that the water flows over, the more we can kind of reduce the amount of pollutants that are transported downstream into receiving water bodies. In order to do this, we'll utilize wasted space, so like rooftops, as a prime example. We'll increase the amount of pervious areas. Again, there's no reason why parking lots can't be pervious. We'll allow that water to infiltrate into the ground as opposed to running off. And then also harvest water for non-potable uses. I mean, there's so many uses for water that we have that does not require drinking quality water. I mean, it's kind of silly. And in doing these practices will result in improved water quality, will attenuate, stormwater hydrographs, so we'll reduce the volume, we'll increase the time till the peak. Will also allow us to kind of provide some relief to existing stormwater infrastructure that might be near, capacity. So, the smaller pipes and ponds, may be okay if we're able to reduce the volume within the watershed. All right, so green roofs. So this is a little kind of schematic that kind of shows the basics of what a green roof is, and really it's just a vegetated roof cover. I mean, is the quick and easy of it. I'll just kind of real quick go over the layers here. So obviously we have plants as one of the layers, and then those plants are grown in a specifically designed growth media, which is lightweight, but can also support plant growth. Then we'll have some separation fabrics to kind of separate the different layers. Usually in Florida we use a pollution control layer. I'll talk a little bit about that. I'll talk about that a little bit more in a minute. And then a drainage layer, and then that's on top of a waterproof membrane. Depending on the system you use, if your waterproof membrane is not a rated root barrier, then you need to add a root barrier. However, whenever doing a green roof, I strongly recommend getting a waterproof membrane that is a rated root barrier, because they're very, very meticulous about making sure that those membranes are watertight. But there's not really a way to test the root barrier to see if it's root tight, and roots are very tenacious. So some benefits of green roofs. Obviously, they're aesthetically pleasing, enhance biodiversity. I've seen several birds nesting, and very good for pollinating insects. And of course, I'm sure all of us have heard about the issues with bees and whatnot in recent years. Increased roof life. That's actually a really big one. One of the biggest stresses that waterproof membranes face on a rooftop is thermal expansion and contraction. So basically, in a 24-hour period, you have such a large temperature fluctuation that the materials actually expand and contract. And so what ends up happening is that puts stress on those seams, and then so eventually, they'll become not watertight, and then you get leaks that way. So as an example, we did a test at the university, and we found that a high albedo white, reflective rooftop, would have a temperature fluctuation within a 24-hour period of about 75 degrees Fahrenheit. Underneath the green roof, it had a temperature fluctuation of 5 degrees. So I mean, that's a really big difference. They say a lot in Europe that green roofs will last 50 years or longer, and that right there is one of the main reasons. Also reduce urban heat island effect. That's actually why green roofs were started in Chicago many years ago in the late 90s, mid to late 90s. I don't know if you guys remember, there's a bad heat wave over there. Several people died, and they attributed it to the urban heat island effect. Increased pervious area, why we're here. And then attenuate hydrographs. So speaking of hydrographs, so here is an example of basically a control roof hydrograph, so a regular conventional roof compared to a green roof hydrograph. These were done on kind of smaller test plots, but the idea is still the same. So you can see, almost as soon as we start applying water, we're starting to get runoff from our control roof. So, that's kind of the old way of doing things. Is it's not so much about, holding water and treating it and then releasing it slowly. It's all about, gathering up all the water you can as quickly as you can and pushing it downstream as fast as you can so that there's not any flooding issues upstream. That falls in line with that. However, you can see this one is the green roof, so we don't even start getting runoff until several minutes after the storm starts, and we have a nice smooth shape to the hydrograph, and then we've not only significantly reduced the peak by about half, but we've also, the volume is the area under the curve here, and you can see that we've also significantly reduced the volume that comes off of that roof as well. And then not to mention the fact that we've increased this lag as well, so kind of the control roof is very flashy. Water comes in, water comes out very quickly. But the green roof, water comes in, it takes a while for it to move through all those layers until it gets to the point of drainage, and then it kind of slowly releases as it goes by. So now if you think about stormwater infrastructure, you can imagine that, if you're in a city setting or an urban setting and you have all of these areas draining to this infrastructure all at once, how that can cause some flooding issues. But if you're able to attenuate some of these areas and kind of delay the time at which it hits that infrastructure, that can have a significant impact on flooding. All right, so what about water quality? Well, we are putting a significant amount of organic materials up on the rooftop, so of course there is that potential to leach nitrogen and phosphorus coming off of the roof. So there's a couple ways where we can address this. One is we can use a cistern and we can capture the runoff that comes off of our green roof, and then we can reuse that water for irrigation or of the roof or ground level landscaping or maybe some other applications. The other way is to use a pollution control medium, as something I alluded to earlier when I was showing the cross section. So one of the things, and this was actually part of my master's research when I was at the university, we actually developed a pollution control media called Bowling Gold. That's used specifically for a green roof application where it's a lightweight material, uses recycled automobile tires, and is found to be very effective at removing phosphorus. So here's a little graph that kind of shows some of the water quality results that we got. This is for orthophosphate. So over here on the left, these are green roofs with gold and gold pollution control layer. The four on the left are with vegetation, and these four are without. The two red ones are control roofs. And then over here we have green roofs with just the growth media layer. And so these four are without vegetation, and these four are with. So a couple of things jump out at you right away, and that is, as well, vegetation seems to have a pretty good effect, as far as reducing the amount of phosphorus that comes off. The other thing is wow, this pollution control media seems to basically reduce concentrations to what we would see off of a control roof. I mean, statistically, there's no difference between those. And then if we incorporate into that the volume reduction that's achieved by the green roof, we're looking at removals essentially equivalent to whatever that volume reduction is. Nitrogen. So this is for nitrate, kind of the same setup, but you can see basically everything's much lower with the green roofs than what it is for the control roof. And essentially the source for the nitrogen in the control roofs is atmospheric deposition. So NOx is a combustion byproduct, so it's around. Anyways, again, so you can see concentration-wise, we're already much less than what the control roof is. And then again, if we incorporate the volume reduction that's achieved with the green roof, then we're really making a significant improvement as far as nitrate. So I'm going to show you a couple of green roofs now. So this is actually the first successful one that I'm aware of in the state of Florida. And this was actually my master's project, and this is the UCF green roof. So this is when we first planted it back in 2005. Wow. So that was a long time ago. And then here it is just a year later. So we got full coverage in less than a year. I mean, you can see all these flowers of Lardy, and actually, if you walk along the beach, I'm sure you'll see several of these flowers over there. So native, Florida native plant. And again, like I said, pollinators love this stuff. I mean, every time we went up there, we saw tons of pollinators, and very, very nice, very nice. This here is over in Charlotte County Stadium. So this is a Tampa Bay Rays spring training facility down in Port Charlotte. It was a very nice area, but they wanted to do a little educational thing up there, so we did a little green roof kind of demonstration for them over there. This here is a project that we did in Claremont. This is the Honda headquarters building over there in Claremont, Florida. It's a little over 5,000 square feet. It's a LEED Platinum building. Actually, a very cool project. Had a little over 5,000 square foot green roof. They had a lot of photovoltaic panels. They captured stormwater off of the roofs and reused it for washing cars. They had permeable pavers, and not to mention a bunch of other stuff inside of the building. If you're in the area, I recommend you check it out. But 4 months later, this is what it looks like. It's still going strong, looks fantastic, and the guys over at Honda are very happy with it. All right, so I will shift gears a little bit, and we'll talk about pervious and permeable pavements. So this here is a picture of the lab at UCF that I used to run, and we had, I mean, really, I think every single pervious pavement that you can imagine. Everybody wanted to get it tested. So this shows FlexiPave. These are Old Castle pavers. This is pervious concrete. This picture is before we had porous asphalt over here, and then a number of other different paver blocks. But basically, this is kind of an easy thing to do. We can replace parking with pervious surfaces. So rather than capturing all that stormwater and sending it off to a pond, why not just let it infiltrate at the source? Again, you're reducing pollutants. Many times, the microbial community in the soil is more than capable of handling any pollutants that are going to directly infiltrate into it. And also that stormwater is not running off over large areas of impervious surface picking up pollutants. They also contain many different layers, and there's a ton of different designs for these systems, and this is just one. So we did some testing with Pave Drain down at the lab, and so this is one of their typical cross sections. Where you have the blocks over about 6 inches of number 57 stone, and then they have their own little, it's like a 2-inch high void space drain cell. So again, just a way to increase the storage that you're getting under your parking area. This is another one. This is a little bit more extreme of an example where they have 6 inches of 57 stone, and then a structural grid, and they'll do 12 inches of 57 stone, and then a large kind of again, a high void space area. One thing I do want to kind of point out, though, is if you can kind of see these vertical lines that are going through the system. I'm going to talk about those in a minute, but basically that's how we monitor, the performance of these systems with time. We have to have a way to verify performance. Water management districts aren't going to just let us put something in and then, there's no accountability for, oh, well, you don't have to maintain it, and you don't have to, you have to maintain these things. You have to maintain everything. If it was built by man, you have to maintain it. Bottom line. Anyway, so St. John's, they require a minimum of 2 inch per hour infiltration rate into the parent earth soils. And basically where that number came from is we have to recover the system within 72 hours so that it's able to get, kind of the next rainfall event. Performance does vary over time. As it gets loaded with sediment, as you can imagine, it will slow your infiltration rate. But you have all those different layers. So depending on what your system looks like, you're going to have different areas of interest. So typically your bottleneck is going to occur at that interface between the bottom of your system and the parent earth soils. However, sometimes depending on the surface layer you could have a bottleneck up there. So if you remember on that earlier picture, that's why we have a short ring that goes in there, so that measures the surface, and then we have a long ring that goes all the way into the parent soils, and that measures the recovery of the system, so how quick water is able to get into the ground. And this is called an embedded ring infiltrometer kit, named after the student who came up with it, whose name is Eric. Basically, it's an in situ test. It's non-destructive. It's repeatable, and it also ensures that water is able to go all the way through the system. There's an ASTM test out there, and the name of it is escaping me at the moment. But essentially, you go in, you put a ring down, you put permeable putty around it. But as soon as water goes into the system, if there's any kind of resistance to a vertical flow, it's going to go laterally. And so it's not going to give you a true reading of what's actually going into the ground. This test actually tells you what is going into the ground, or even what is going into the system, depending on how deep your ring goes. This is just a little section of that. So again, you can see the ring is embedded so you can drive over it and everything. It's not in the way, and it allows the pavement to function as it's intended. And then you come in, you add a little test collar, and then you're able to do a constant head. I say permeability, but really it's an infiltration test. And then this here is the measuring reservoir. So essentially, you have all these lines here, and those have been calibrated to be equivalent to, for this one is 1/2 inch and a 6 inch diameter pipe, which is the diameter pipe that's used for that infiltration testing. What about clogging? Well, we did a lot of tests with clogging. Obviously, this is not something that you would normally see in the field. But we wanted to kind of simulate, well, what happens at the end of the life of these systems when they've been in the ground for 20 plus years, or maybe there is a spill of some variety that happened on there. Can these systems be rejuvenated so that they're still able to perform? And the answer is yes, they can. So we were able to use vacuum trucks, and they were quite effective. And we were also able, Pave Drain had their own little kind of vacuum system, and that was also very effective. Now, one thing to note, though, is, conditions need to be favorable. So if you're in a condition like this, where it's the soil's just kind of damp, it's kind of sticky, it's not gonna rejuvenate very well. It's not gonna come out of your system. However, if it's completely saturated or completely dry, that's a fantastic time to go vacuum. Really, saturated is the way to go, because you're almost never gonna come across a condition where it's completely dry. So usually when it's raining, that's the time to send your guys out to do the vacuuming of those pavements. And since they can't do the regular impermeable pavements anyways, it gives them something to do. So here's just some results here. So basically, this is a short ring. Starts out super fast. We load it with sediment. It slows down. I should also mention that the operator of the vacuum is very important. So we had kind of our first vacuum, and it didn't really do very well. So then we had another vacuum, and then it did rejuvenate the system back up. Then we clogged it again. This time we clogged it. The first time was a sandy soil, and the second time we did it, it was a silty sandy soil, or Ashno A24. But then we rejuvenated it and boom, right back up. Okay, so these systems can clog, but they can also be rejuvenated. This here is showing the long test, so this is the system recovery. So again, and it should be noted too that there's a lot of natural variability that occurs as well. I mean, and you'll see the same thing with natural soils. I mean, you can go measure the same plot, 20 times in 20 days, and you'll get a different measurement every time. I mean, there's just a lot of natural variability to it. But so, that's kind of what's going on here. But anyways, we loaded it slow, vacuum it. This one they happened to do well. It went back up, vacuumed it again, it went up again, clogged it. But again, the silty soils is a little bit tricky because it travels deeper down into the system, okay? So it's not as easy to pull back out. You'll notice that, we got up well above the 2 inch per hour minimum that St. John's requires, but it didn't rejuvenate to the extent that it did after the sandy soils. All right, stormwater harvesting. So why do stormwater harvesting? Potable water is a valuable resource. We want to reduce our demand on potable water. And again, I mentioned earlier, there's so many uses that we have where we don't need drinking quality water. I mean, toilet flushing. I mean, unless your dog's drinking out of that thing all the time, we do not need drinking water in our toilets to flush toilets. That's ridiculous. Irrigation, plants don't care. They don't need drinking water. Cooling tower water, that's another one. You do tend to need a little bit higher quality water for cooling tower water to prevent scaling, but there's treatment that can be done in order to ensure that the water is of a sufficient quality. It still doesn't need to be drinking quality water. Washing clothes too. And again, if you're using that stormwater, you're reducing the volume that goes downstream, and a reduction in volume equals a reduction in mass. So what do? Use cisterns, capture that water. You can even use existing wet detention ponds. So again, we talked earlier about stormwater infrastructure that's near capacity. Well, if you're able to take water out of that stormwater pond and use it for irrigation or some other beneficial use, well, you're creating capacity in that pond. Also, there's underground storage, and this is actually something we're doing with Geosyntec, where we have a research project. It's an internally funded project where we're going to do a underground stormwater harvesting system. And basically, it's you have a storage reservoir here, which is wrapped in an impermeable liner. Okay. Wrapped in an impermeable liner, so water flows in, fills up. We have a control structure here, but rather than when it overflows, it going right to the downstream infrastructure, it goes instead to an underground exfiltration area. So only when that backs up does this system then knock off and then go to your downstream stormwater system. So another thing we can do to further improve the performance of this is using real-time controls and real-time weather forecasting. And there's a company that we're going to be working with called Opti that is going to control that. And so basically what they do is using real-time forecasting is they say, all right, well, it's going to rain in an hour or whatever, about a half an inch. So they will empty out the system that much, that equivalent volume, so that when it rains, it's able to capture that full amount that that it rains. And in this way, we're infiltrating water before the storm even gets here. And if it does happen to overflow and go downstream, that's fine because our downstream system is empty anyways because it hasn't rained yet. So I mean, it's just another way to further increase the efficiency of these systems and to reduce stress to overstressed systems. And by the way, this did pass AASHTO HS20 loading, so it can go under parking lots and stuff. And then my last thing, sorry, I don't want to move on. We have this is actually one of the first projects I work on at the university. It's called the Florida Showcase Green Environment. It's down in the Atlantic, which is over by Melbourne. So basically, again, a really, really cool project. We did a lot of integrated water systems. We have 5 different green roof areas on there. They did a lot of photovoltaic stuff. We did a Bowl and Gold bioswale for their overflow. We did, what else did we do? A bunch of stuff. So anyways, over here is a little schematic of kind of their house and what's going on with their water system. So we're capturing all of the rainfall that falls on their rooftop. We capture that, and that goes to 3 1,500-gallon cisterns that are buried in their backyard. That water is then used to irrigate the green roof areas as well as the ground level landscaping. And they also use it to flush their toilets and to wash their clothes. They also capture all of the gray water within the house into those same cisterns. Obviously, we have to treat it, and so we do some ozone treatment of that. And then we have well makeup water, which goes into it. So just a battery's dead. Can somebody switch to the next slide for me? All right, so here's a picture of the house when it's mostly done. So they did a pervious pavement driveway there, green roof area on the top. You can see on the top right, there's some green roof areas. The cisterns there, green roof area. And this actually here, this is kind of cool. They have the pump house there for their pool. There's a fountain that goes down over that. We did the green roof behind it. We have some like railroad vine that kind of like grows up into it, and so that's really cool. And then over next to that, there's the bioswale, which has again a golden gold media to kind of help remove pollutants. And then the entire landscape is Florida friendly, so really neat project. Next slide, please. Thank you. Next. All right, so the quick of it, green roof, pervious pavements, and stormwater harvesting are all effective ways to not only reduce the volume of stormwater runoff leaving your site, but also to improve the quality of water. Thank you. Next. And then all of these BMPs offer you some level of flood protection, but mainly water quality improvement, cost savings, and sometimes, more importantly, good PR. There you go. Yeah.
I have one under green roofs. I see you're planting certain like individual species or different species in different areas. Are you doing to maintain that, or are you letting it go wild after that?
It depends on the roof, and it depends on the building owner. So a lot of times the plants will kind of migrate to where they want to go naturally anyways. You know, in some respects, you kind of have to let them do that. However, you can't maintain them to keep plants in a certain area. But usually when you're planting it, you want to kind of put your more water-loving plants closer to your drains, and you want to do your more, your drier plants. You want to put those kind of towards the perimeter of the roof where they're going to stay. Well, unless you have scuppers, but towards the drier areas of your roof. So you kind of want to look at the roof and kind of figure out what your different zones are going to be, and also kind of figure out what your different light sources are. I don't claim to be a botanist, so I will talk to my plant people and say, hey guys, what do you think about this? And what do you think about these plant species? But one of the things we do is we look at kind of the coastal communities, because those plants are already very used to living in kind of drier environments, low nutrient, well drained soils, which is very similar to the types of conditions that they're going to see up on top of the roof. Anybody else? Oh, all right. Thank you guys very much.